Milo, Susie, and Angelina need to design a way to communicate with another group. One way is to use light. We first need to understand how light works to create a design that solves their problem. Light travels from a source, bounces off of an object, and then enters our eyes for us to see it. In this activity, we will explore the differences between light and dark. You will want to have your launch log pages 8 and 9 on hand. You will find these in your packet, and the reason why you want them is because we're going to be filling them in as we watch this video.
Welcome to the Exploring Light learning experience. In this presentation, we will explore a variety of sources and properties of light. The sun is our most important source of light. Humans have used other sources of light, including fire and light bulbs. How many lights can you count in your classroom? Please record the number of lights in your launch log.
So this is our first question, and I want you to count how many lights are in your room. So I'll count how many are in my room right now, but I want you to count how many are in your room at home. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 12 lights in my room. How many do you have? Whatever number you have, you are going to write that here. So how many lights do you have in your room? Again, I have 12 in the classroom, but how many do you have at home? Go ahead and write this here. Pause the video if you need to, otherwise we're going to continue on.
Lightning is a source of light during severe storms. Sound travels slower through the air than light, which is why you see lightning before you hear thunder. If you hear thunder 5 seconds after you see the flash of lightning, the bolt hit the ground about a mile from where you are. How long would it take to hear thunder from a lightning strike 2 miles away? Write your answer in your launch log.
So we're going to go back to our launch log again, and we're on page number 8, and it says, how far away did lightning strike if you hear thunder 5 seconds after you see the spark? In the presentation, they said 1 mile. Go ahead and write that, 1 mile. Now we're going to do a little bit of math. How long would it take to hear thunder from a lightning strike 2 miles away? Well, you'll notice that they doubled the number of miles, so we're going to double the number of seconds. So what's 5 plus 5? 10 seconds if the lightning strike is 2 miles away. Okay, we'll keep on listening. Again, pause if you need to, but we're going to continue on.
We see objects around us because light travels from the sun or another source and bounces off the object and into our eyes. But how do we see a shadow? What is a shadow made of? Shadows are not made of anything. We see them where light can't reach because an object is in the way. In this photo, the boy and his bicycle are blocking the light from the sun. In your launch log, draw a picture of the sun, you, and your shadow.
I want to point out that in this picture, the sun is over here. Here is the boy, and his shadow's here. His body is blocking the sun's light, and that's what creates a shadow. So we're going to draw a picture here. It says draw a picture below with the sun, you, and your shadow. So we're going to start with the sun, and we're going to start with the sun on this side of the paper. So here's my sun. Then I'm going to draw me. And then I'm going to draw my shadow, which is going to be on the ground. And you know, when you see shadows, I'll go back to that picture. Notice that it's fully dark. So that's why I'm coloring this in really well. So this is my shadow. Okay, again, it's sun, then you, then your shadow. It doesn't make sense for me to have my shadow over here because what's happening is the sun's light hits my body and I'm blocking the sun's light, and that's what creates a shadow. If my shadow was over here, it's not possible because the sun isn't being blocked over here. The sun is blocked on this side. Go ahead and pause the video if you need to. We will continue on to page 9 in our launch log.
Take a close look at this astronaut's helmet. This is an image of astronaut Buzz Aldrin as he walks on the surface of the moon. Can you see the astronaut who took the photograph? If you look closely at the helmet, you can see astronaut Neil Armstrong in the reflection. Reflection is the return of light or sound waves from a surface. Any smooth or shiny surface can create a reflection. The lake in this image is reflecting the fireworks in the sky. Now that you have learned about reflection, think about which of the following objects would make the best mirror: ice, sand, or a leaf. Write your answer in your launch log and explain your choice.
Let's think about these 3 options. Let's start with the leaf. When we look at a leaf, does it have a smooth surface like a lake or a piece of glass? No, it will have rough edges. You can see that here. And you can also see that it has indentations on the leaf. So a leaf does not have a very smooth surface. Let's take a look at the sand. Think about how sand would feel in your hand. Is it a smooth surface? No, it's really gritty. So sand could not reflect like the lake can. Let's think about ice. Ice is smooth and it is pretty slick on the sides. And so with that smooth surface of the ice, it is the best option to be a mirror. Remember, a mirror is a way of reflection. So let's go to our launch log now. We're going to page 9, and we are going to add that idea in here. So we're going to say ice, and I've filled in some of this for you. So because it has the, and then here we need to write smoothest surface. I will make this a different color so it's easier for us to know what we need to write. Ice because it has the smoothest surface for light to bounce off of. It needs a smooth surface for light to bounce off of it. So you need to fill in the blanks. Ice, it has the smoothest surface, and then for light to bounce off of. Pause the video if you need to finish filling in these blanks. We will continue on.
Color is the way that objects appear different because of light reflected by the object. We see colors such as brown, red, yellow, and blue because of how the light bounces off of the object. Colors of light can be mixed together similar to how you mix paint. Unlike paint, when red, blue, and green light are mixed together, you see white light. Answer the questions about mixing colors of light in your launch log before you continue.
The question says, what color do you see when the colors of red, blue, and green are mixed together? What did the video say? You see a white light, so you need to write white on this line.
The color white is made up of many different wavelengths of light. Light slows down just a little when it travels through something more dense. When light travels from air into water or glass, it slows down and looks bent. The colors that make up white light slow to different speeds, so the colors separate in a process called refraction. Refraction is the process that reveals a rainbow. Complete this sentence in your lunch log. We see an object when light bounces off of it and enters our eye.
Let's fill that in. So, we see an object when light bounces off of it and enters our eyes. So you need to fill that in. We see an object when light bounces off of it and enters our eye. Pause the video if you need to.
Congratulations! You have now completed the Exploring Light learning experience.
All right, the next part that we're going to do is I need for you to rip a piece of paper, just a tiny piece of paper, and you're going to stick it in your hand. And what we're going to do is you're going to set that piece of paper in the palm of your hand. Just like this. And I want you to describe the paper to me. What does it look like? Well, what I see is it's orange. My paper's orange. It's small and it fits in my palm. It looks kind of almost square-like. Has a curved edge here. Now we're going to put our hands together and part your thumb slightly so only a small amount of light enters your hand. So kind of like this. Do you see how that's only a small amount of light entering? Then I want you to look through that and describe what you see on that piece of paper. Are you able to see the paper? Maybe a little bit. What if you close your palms even tighter so it's only a little peephole? Now look in. Can you see a piece of paper anymore? We can't see the paper in complete darkness. Just think about when you're in your bedroom. If you had no lights on in your bedroom, would you be able to see? No. Well, did the stuff in your bedroom disappear? No, the stuff in your bedroom is still there. Did the piece of paper disappear from my hand? No, it's still there. It was just in complete darkness. We're going to go to our launch log now. And again, we're on page 9 still. It says, why can you not see objects in total darkness? Well, we can't see them because light must bounce off. So we add that idea. Bounce off an object. Into our eyes. If light cannot bounce off of the object, we are unable to see it. So it has to bounce off of an object for us to see it. So go ahead and add those 2 words to that sentence. I'll change the color here. And again, I'll say that one more time. Read it with me. Light must bounce off an object into our eyes. So when something's in total darkness, there is no light to bounce off of anything. So that's why we can't see it.